There we
You're
go.
already recording, Brian.
Well, that's that autopilot. That it's kind of a weird app. It does transcriptions of the audio to text, and it's actually pretty good. But it's installed itself automatically, and I've just left it. It almost feels like a virus though, because it did kind of come in automatically. But well, I tell you what, everyone, we're going to go ahead and get started here. You can see the agenda here. Um, I had something else planned that has fallen through, so we may not end up going the full hour and a half, and so you can all head out to Miller time or dinner, maybe a little bit earlier. But I won't go into anything here. We'll just dive right in. All right. So we talked once before, I think it was last month, about this. Colorado hydrogen infrastructure study that the Colorado Energy Office is doing. And what they're trying to do is collect some market research. You can see, it says that there for an upcoming study. It's like a study to do the study, I guess you could say. And then there'll be a grant, hopefully forthcoming from that. So this was due March 1st. The RFI is right here at this tiny URL .com site. I created a shortcut for you because it was kind of a long URL. That got extended to March 15th, which of course has passed. So too late to input on this yet. But as I said, this RFI is to gather information to actually do the study. It's sometime in 2024. And you can read that. It's to inform the design, development, and implementation of a Colorado hydrogen fueling infrastructure grant, which is called SHINE. And that stands for Sustainable Hydrogen Investments for a New Economy. And as I said, the intention there is to fund some fuel stations. Excuse me a second. I'm looking real quick to see who else is on. Maria's on. I don't know, Maria, do you want to comment at all on this? I don't know that you need to, but
Yeah, so the purpose of the RFI is to inform a study to stand up a grant program. That grant program is going to be offered through the Community Access Enterprise. That's one of 4 state enterprises at the state that are funded by fees on residential deliveries and shared rides across the state. There's no sunset for that fund. So this grant program has a pretty long timeline and a pretty steady budget associated with it. So that's why the state is doing its due diligence in research and analysis to stand the program up. And it has, Brian mentioned, the deadline has passed. We did get some good response, and we'll be analyzing that towards the development of the study.
okay. Thanks, Maria. We're going to talk a little bit more about those so-called enterprises, the community access enterprise, the fleet enterprise, and the transit enterprise as we get into some of the other things here. So you'll hear a little bit more about that. So I just wanted to give you a little bit of an overview of what this RFI was asking. It had some technical and some financial parts to it. We had asked for some comparisons between moving hydrogen as a gas versus as a liquid. Other questions about hydrogen supply, transport, and delivery methods. Looking for information about safety, liability, insurance, and so forth. Also looking for a little bit of information about coordinating with utilities. If we want to do hydrogen generation on site using electrolysis, most likely want to use the grid for that. And then also looking for some information about permitting and zoning and connecting with utilities and so forth. More on the financial side, there were questions about site costs, construction, infrastructure, operation and maintenance costs. And then also asking for any input about the grant incentive structure. How should maybe that be set up, and timelines and so forth. So I put together a pretty comprehensive response. It was about 26 pages, I think. And one of the things that I really wanted to focus on was just the basic business fundamentals of hydrogen fueling, a cost price analysis. I assume there's people out there that are kind of looking at this, but I don't see a lot of this in any of the information that I really see coming across the web. So I think one of the first things is that we really do have to think about hydrogen, at least for transportation, competing with petroleum. Um, Maybe there's some willingness early on for people to pay a little extra, but in the long run, we've really got to compete because people are going to be deciding, and people, whether it's individuals or it's businesses like fleets and so forth, they're going to be deciding, can I, do I even want to move away from a petroleum vehicle to some kind of a zero emission vehicle? Um, Individuals might say, well, I'm willing to pay a little extra, but businesses by and large are going to be looking at the bottom line and thinking, can I really afford to do this? So, one of the things that I looked at was the cost to move hydrogen. We can certainly make hydrogen on site using electrolysis, but that may be more expensive than other sources of hydrogen. And I'm going to get into all this. Um, I gave an analysis of the cost for on-site electrolysis, and then also talked about the fact that we have got to come up with some kind of a source of low-cost hydrogen that's way cheaper than electrolysis. And things like hydrogen wells and underground hydrogen generation, and that underground hydrogen generation is the proton technologies process of taking old oil wells, injecting oxygen, and bringing up hydrogen. And proton technologies has for quite some time now talked about getting to around 30 cents, 25 to 50 cents, but 30 cents a kilogram. And that's what it's going to take in order to have hydrogen compete with petroleum for transportation. So another thing that I looked at was suggestions around the rules and regulations using the grid to exchange that energy. I've talked before. I did a presentation on this meeting back in July about the fallacy of this so-called temporal matching, where a lot of the environmental groups seem to think that the energy production and use has to be done at the same time, which it absolutely does not, because we're talking about energy, and energy is power times time. So it already contains a time element. It's already a commodity. It's already been packetized, if you will, and they don't have to happen at the same time, as long as they are tracked between the source and the load, and at least within some billing interval. So I put in some information about that. All right, so pricing hydrogen. Let's start there to talk about what hydrogen needs to cost for transportation. And I think it goes without saying that if you're going to try to sell a new product, whether it's a cell phone or a washing machine or a car or whatever, and you're trying to convince people to move from what they have now to something new, it's got to offer the same or better cost, performance, and convenience as what they have today, or people just aren't going to do it. And that's, I think, one of the drawbacks in some ways to battery vehicles, because people say, on a long trip, I got to worry about charging. What if I'm caught out, with a extension on my daily trip and I don't have enough energy and I've got to stop to charge? That's a big issue. So we've got to think about that cost, performance, and convenience being the same for fuel cell vehicles as well as for battery vehicles. Now, when hydrogen fuel cell vehicles are deployed at scale, they're going to have the same or better performance and convenience as petroleum. And of course, that's assuming we've got some place to fuel them, which we're working on. And we've got to make the pricing basically the same or better on a cost per mile basis as gasoline or diesel. And I'm going to explain why I'm saying cost per mile. And that's because it's based on the vehicle efficiency. I think most of us on this call probably know that fuel cell vehicles get quite better miles per kilogram than their counterparts in the gasoline or diesel world do in miles per gallon. So that's part of the equation. But that varies by class. So this table that I've got here, and let me put up the EER translation here, basically shows that for a given gasoline vehicle, if you have a very similar vehicle that runs on hydrogen, it's going to have about 2.5 times. And let me turn on my laser pointer here, 2.5 times the range as the gasoline vehicle. So basically what that means is that if gasoline is priced at 3.50 a gallon and you're trying to compete uh, with a light or medium duty hydrogen vehicle, you can ask $8.75 a kilogram. And to the user, their cost per mile is going to be the same. Now, as it turns out, diesel vehicles are a little bit less efficient. Well, shouldn't say they're less efficient. Diesel has more energy in it than gasoline does. So the difference between a diesel vehicle and hydrogen is only 1.9. But where we start running into some problems is that for the heavy duty, for the Class 8 vehicles, right now, the energy efficiency ratio is about 1.1. Now, it's may get up to some of the reading I've done is maybe in the 1.3 range, which will help a little bit. But basically, what that means is that you can't ask a lot more dollars per kilogram for hydrogen for these type of vehicles than for the diesel. So that's an issue we have to deal with. And you don't hear that spoken too often. People say, oh, heavy duty vehicles, that's really the way to go with hydrogen. Well, yeah, but the business case is a little tougher. But I think we can get there and we'll talk to that. So, clean hydrogen sourcing. Well, I think it goes without saying that our sources of hydrogen need to be greenhouse gas free, and that's both methane and carbon dioxide. Because frankly, the world wouldn't bother using hydrogen if it weren't for the need to eliminate those greenhouse gases. So I use the word clean rather than renewable or rather than green because there are sources of hydrogen that are not renewable, but they are clean. For example, the underground hydrogen generation using the proton technologies process. So I'm going to use the word clean, even though it's a little bit, sounds kind of generic, but it's a specific usage here. So the source is, of course, electrolysis of water, and then natural hydrogen wells, and then underground hydrogen generation. And again, that's that Proton Technologies process. And by the way, Proton has got a new website. I don't know if any of you have tried to find them, but it's the new website is just protonh2.com. And last time I checked, their old website for some reason doesn't link to this new one. So be aware of that. All right. Come on, there we go. So what are the costs for each of these sources? Well, what I'm going to do now is go into some of my analysis, which looks at how do we get these sources of hydrogen? What do we have to do? And then we'll talk about the cost kind of at the end. So on-site hydrogen generation, a lot of you have seen this diagram before. I've put this up. Basically, the green blocks show you that for an on-site system, you'd have an electrolyzer, some kind of compression, gaseous hydrogen storage, and then some kind of a chiller for the 700 bar. And then, of course, the balance of plant that goes along with it. For moving hydrogen as a liquid, now I'm assuming, because I think this is the only way we're going to get to the cost targets, that we're going to somehow develop some kind of a well, whether it's using an old petroleum well and pulling hydrogen out of that, or just directly a hydrogen well, like we talked about last month with Jeff Ellis when he was on the call. And I'm going to assume that that's 30 cents per kilogram all in for whatever capital equipment payoff and return on investment you've got going, other operational expenses like electricity and so forth. So bringing that in, of course, what you've got to do is you've got to liquefy that hydrogen. So we've got a block here to liquefy that. And then you've got a dewar. And on the tank or the dewar here, I'm showing a heat pump because I'm assuming that this is an active system that keeps that liquid hydrogen cold so you don't get boil off. Then obviously you're going to have to put it in a truck and send it somewhere, put it in another tank with another heat pump. And then what's typically done on the more efficient systems is to use that. I guess I can't really call it energy, but the negative energy maybe that you've got in that very cold liquid hydrogen to basically create compression to get you up to the pressures that you need to be for dispensing, as well as for 700 bar, that's got to be dispensed at minus 40 degrees. And so you can use that cold, I guess I'll say, that you've got there to do that. So this whole system of liquefaction or liquefaction, the tanks, the trucks, and so forth, I've basically done an estimate on what that looks like to try to compare that with other ways of doing this. All right, so another way that you can move hydrogen is as ammonia. And in that case, again, we start with a well. We basically take nitrogen out of the air and the hydrogen that we've got from our well and make that into ammonia, which is NH3. Again, just like with the liquid, you'd have to put it in a truck, move it. You got tanks on both ends to store it. And then with the case of the ammonia, you've got to basically crack that back to hydrogen and then compress it for your dispensing. All right. And then another way you can move hydrogen is using liquid organic hydrogen carriers, things like toluene. And what happens there is you take the hydrogen, you combine it with your LOHC compound, which is reusable, put that in storage, then you can move that using a truck. Again, put it in storage where you're going to use it. And then that's got to be cracked back. And I'm calling that process dehydrogenation here to get the hydrogen back out of it. So it seems like fairly complicated, but it's not really all that much more expensive than ammonia or liquid. And I'll show you those numbers here in a minute. And indeed, you've got to recycle this, it's shown in orange here, but the liquid organic hydrogen compound material. But you've got a truck making a loop anyway. So it can bring the LOHC to the station. And then that same truck could load up with the spent or the dehydrogenated LOHC and take that back. So I don't really see that as a drawback, having that circular path for that compound. All right. So that's basically been kind of the what this looks like. Now let's talk about how these numbers all kind of stack up as far as the price we want to get to, what it costs, and to some kind of summary. So I just showed you this graph a minute ago. This is a comparison of the what we think we'd need to get to as a target sales price for hydrogen based on the different classes of vehicles, the light and medium duty gasoline, light medium duty diesel, and the heavy duty diesel. Um, the since I started doing this, prices on fuel have dropped a little bit. So these, I don't know, this varies, but based on that, we'd like to get to 875 at least for gasoline, light duty and medium duty vehicles. And we may need to get as low as 440 a kilogram for the heavy duty diesel. All right, so here's what the cost roll up looks like for these different methods of liquid, hydrogen, the LOHC, ammonia, and on-site electrolysis. So what I tried to do here, and I really want to emphasize this estimated because I had good data for ammonia and on-site electrolysis. I did not really have good data for the CapEx for liquid hydrogen and LOHC, but I put this out for the Energy Office so that if they like this approach, certainly they've got kind of a straw man here to go get some quotes on what this really would cost. But my estimates were that the capital equipment, and let me back up. So again, the capital equipment would be things like the hydrogenation, the dehydrogenation, the trucks, the tanks, and all those kind of things. That's really what I'm talking about here for CapEx. And I made the assumption that as we are starting today, we're starting from scratch. So if we want to do this, we're going to have to probably go out and develop a well. We're probably going to have to go out and get the equipment to basically put the hydrogen into a form that we can transport. The trucks, we're going to have to operate those as well. So that's all rolled in here. And you might say, well, I would sub that out to like a Linde or an Air Products or something to do. Well, they'd have some of that same expense, and that would probably be baked into their price that they're selling the hydrogen for. So I think this is a fair, and at least it's a kind of a level way to compare these different methods. So we start out, we've got some amount of capital equipment. It's up in the millions of dollars to do this. I'm assuming that we got maybe funding from venture capitalists or something. and that we've got to pay a debt service on that CapEx. And the way I calculated this was a rule of thumb is generally um, that an investor wants to double their money in 10 years. So I basically worked this CapEx debt service as okay, we got to repay back 2 times 3.8 million in 10 years based on the amount of hydrogen we're moving around. What does that work out to per kilogram? All right. So that's where that comes from. OpEx, that's basically either energy or raw material. I guess if you were doing SMR, you'd have a natural gas price, but for the most part here, this is really just energy costs. And then transport costs, that's this CapEx added together with the OpEx is this. So 240 plus 204 is 444. You can see that math. Then I'm assuming that we've got 30 cents a kilogram hydrogen at a well, and that comes out to this total cost per kilogram for liquid hydrogen, $4.74, using LOHC, 617, using ammonia, 751, and then on-site electrolysis is 875. So what we want to do here is we want to say, all right, based on these costs, how does that compare to our targets where we want to get? Well, so I've got a graphic here to kind of roll that all together, but the check marks here indicate where the basically the target sales price is at least as big as what our cost is. So it's probably pretty easy to see for the end cases here. So in the case of electrolysis, um, we want to sell it for 875 or less. Lo and behold, just coincidentally, that happened to work out to be that's what that costs. So that works for light duty, medium duty gasoline vehicles. Um, However, for the light and medium duty diesel and the heavy duty diesel, we're probably going to have to resort to delivered hydrogen. And so you can see that that works out. But as I pointed out earlier, it's still a little bit of a struggle to get to the heavy duty price target, even with liquid hydrogen. Now, maybe if we go to a vendor like Gen H2 or Chart and say, look, get your pencil really sharp. We want to try to find a way to deliver liquid hydrogen based on this well that we've got over here for 440 or less. They might be able to do it, but I think there's a little bit of a challenge there. All right, so I've been talking a lot. I want to pause for a minute here and see if I don't think anybody's got their hand up, but does anybody have any comments or questions right now?
Yeah, Brian, this is Keith Whipke. Just had a question about the 1.1x, where you got that, or is that an average or something?
Well, that is the best that I can come up with looking at some of the published things that CARB has done. Also, currently, that's about what Nikola is seeing with their trucks, but it's my understanding they've probably got some excess weight in their trucks they hope to eliminate, so that should go up. So as I said, the things I've read, 1.3 is about as good as we get. I don't know, Keith, have you seen better numbers than that?
No, actually, I just knew that it wasn't as good as light duty, and so that's why I was so curious where to get good information on that. And of course, heavy duty isn't just heavy duty, right? There's heavy duty long haul from New York to LA. There's heavy duty that's going from a warehouse to downtown Denver. I mean, there's like the duty cycle impact of hybridization and things like that are majorly different across the various spectrum. So, but I think certainly for long haul diesel, that's where you've got your biggest challenge, because you get those however many gear transmissions that just get you dialed right in at that peak efficiency of diesel combustion, and you can't get much better than that, extracting the energy into mechanical torque.
Yeah, and that's a really good point. And Frank, I see your hand. I'll get to you in a second, but that whole issue of I guess I'll call it duty cycle. In other words, how the power band or how how much pedal to the metal that you've got in your vehicles. And it's my understanding, talking with Cummins and some other folks, that the reason this heavy duty is a lower number is because the light and medium duty vehicles are coasting a lot. I mean, if you think about a lot of us have cars that have got a mileage indicator right on the speedometer. And a lot of times, even on just a flattened level, you're not applying too much power. Whereas these big trucks, because of the weight and also because of the air resistance, I mean, they're towing a big parachute down the road, right? That they are up in a pretty high power band a lot of the time. And that's part of why they're not as efficient. Now, I don't have any better explanation for it than that, but I know this is an issue. All right, Frank, go ahead with your question.
Yeah, so thanks, Brian. And I'm just wondering if production tax credits and investment tax credits play a role across the board here as well, and improving the cost per kilogram. So I just wonder if you considered that as part of this analysis. It would be another potential column or two, perhaps.
Well, that's a really good point, Frank. And I am not taking into account any kind of tax credits or incentives or anything here. This is kind of the raw data. Now, we got to be a little careful there, because if you're going to an investor and saying, "Hey, I want you to invest in my hydrogen station that I'm going to build, and here's what my numbers look like," and I'm assuming all these investment tax credits, the investor may say, "Well, that's great, but what if the political winds change and those tax credits go away? Or what about when the tax credits run out?" We need to really try to get to a point where we've got a viable financial model here that is going to work in the long run. Now, okay, we've got tax credits we know we can use today. Um, but on the other hand, I bet you we can't get to these numbers just yet today, because we're in the early days of a lot of this equipment. Um, the example I've used so many times before is, if we look back, and I actually keep this on my desk here, of prices of technology when it first came out. Like in 1927, the first GE refrigerator in today's money was about $7,400. It didn't even have an ice maker. And then the old Dynatac cell phone, those old brick cell phones, if any of you have seen those are like $11,000 when they first came out. Compact Desk Pro 386, 18 to 30K. I mean, you kind of get the idea, but um, the equipment prices are going to come down. That'll help us meet these numbers, but we're going to have trouble getting even to these today. My internet connection's unstable. I'm going to pause a second. I hope I'm still coming through. So on the one hand, we probably aren't as efficient to get these numbers today. On the other hand, we've got tax credits, so maybe they kind of wash. But really what I was after here, Frank, was to lay out kind of an analysis or a way of thinking or a systems engineering guidance on what do we have to be looking at and where do we have to get? Because when you look at this, you say these numbers barely work, and only if I've got 30 cent a kilogram hydrogen. Guess what? Maybe our main in emphasis here should be to go out and get some hydrogen wells going, so that we've got this cheap source of hydrogen, so we have a ghost of a chance of getting to the financial numbers that we need to get to. Okay, anybody else? Some thoughts? Those are good ones. Thanks, Frank, and thanks, Keith. I just